Hello and welcome back. Today we're going to talk about spin-spin lattice and T2 contrast. So we're going to look at the T2 component of this. In order to understand this, we need to understand what this spin-spin lattice means. And so when we try to understand what we're looking at here, what we're trying to measure is what is happening to protons after we excite them, place them in the transverse plane, and watch their precessional frequencies. All right? We watch them precess in phase and slowly become out of phase. And we graph this out. We actually measure this. We measure what's happening to this decay in the transverse plane. So it's really important to understand what is actually happening from the T2 component. So we're going to draw this. If we were to have a graph, and since we're measuring transverse magnetization, we need to go ahead and place our transverse magnetization on one of our axes here, and we're going to see what happens over a period of time, because remember, we're measuring something. We're measuring the decay of transverse magnetization. Prior to this entire process, we have our hydrogen in the longitudinal plane. They're at rest. We have those hydrogen aligned parallel and anti-parallel to that B0, and we have net magnetism. Right? So those hydrogen are in the longitudinal plane, which means they're not in the transverse plane. So we have 0 transverse magnetization prior to our RF pulse. Now, when I deliver an RF pulse to my patient, I take this magnetization in the longitudinal plane and I drive it all down and I place them in the transverse plane. These hydrogens start to precess in phase in the transverse plane. So we have this vector now, this net magnetism in the transverse plane. Very rapidly, after we excite those hydrogen, we're going to have all this transverse magnetization in the transverse plane, and they're going to have this rapid decay of transverse magnetization after we turn off this transmitter. So we get this rapid decay of transverse magnetization after we turn off our RF transmitter. Right. And let's just say this is adipose tissue or fat. And every tissue will have this unique decay, or this free induction decay. So we're going to go ahead and do this again, but let's say we have fluid. So prior to our excitation, we have no transverse magnetization, and after we deliver this RF pulse, we get all this transverse magnetization. Because we tilt that longitudinal magnetization, we drive that down, and we tilt those protons into the transverse plane, and then we get this decay from fluid. Fat has a very fast decay time based on its molecular structure, and water is going to have a slow decay, a slow free induction decay. Now TE controls T2 contrast, and what we did here is we just graphed out T2 contrast. Now, when I'm trying to understand a T2 time, I need to understand what I'm looking at from the perspective of how much magnetization will I need to lose in order to really replicate or visualize what's happening to the transverse decay of my tissue. So I need to wait for 63% of my magnetization to decay, or when I have 27% left to my image. And then I'm going to try to find a time that I have the largest differences between this two tissues, fat and water. And this would be my TE time. You can see the longer I wait on my TE, the longer I wait this period of time, the more differences I'm going to see in my image. All right? So that's essentially T2 contrast and that spin-spin lattice component to it. They're essentially the same thing. So when we look at T2 contrast, we're measuring the spin-spin lattice and looking at this decay of transverse magnetization over a duration of time. And then, when we use our parameters to select an optimal time to represent this in our image, we're using our TE to identify that period of time to represent the amount of transverse decay in our image. Right? Thank you so much for watching, and I'll see you next time.